So our next talk is by Professor Dachun from Beijing Normal University, and who will speak on ball average characterizations of functions.
Thank you. So first, I would like to thank the organizer and especially Professor Hongdai to invite me to come here. So it's the first time for me to be in England. And second, I would like to say this: in 2017, I gave the same talk in the conference organized in Beijing level. So maybe somebody has already have already know my talk. So the title of my talk is ball average characterizations of function spaces. This is mainly joined with my students. And my talk will have 4 parts. In the first part, I will introduce some pointwise characterizations of Besov and Triebel-Lizorkin spaces with smoothness not greater than 1. And then I will introduce the ball average characterizations of second-order Sobolev spaces, and then ball average characterizations of second-order Besov and Triebel-Lizorkin spaces. And finally, I will give some remarks. Why we wanted to study this subject? Since there exists no differential structure on a general metric magic spaces, so it's still an incompletely solved question how to introduce function spaces with smoothness on such a setting. So what we do now is we try to find some new characterizations of well-known function spaces so that these new characterizations can be used as the definition of the corresponding function spaces on metric magic spaces. So this is the main motivations. I will very first recall some definitions. First, let M be a natural number and Z plus be the positive integers, and P between 1 and infinite. Recall F is belong to the homogeneous superspace W dot MPRN. If and only if F is a Schwartz distribution and the M partial order F belong to LP, and they will define the norm just the sum of this quantity. Such space is called homogeneous because for any positive lambda and any functions in this space, the dilation of this function, the norm, you can get some fact here. So times the original norm of F. So, and for the inhomogeneous superspaces, the definition is a little bit different. We say F belong to WMPRN if and only if F in LP and all the partial derivative F in LP with the order norm of the M. Moreover, then we define the norm F in this space just the sum of all the partial derivatives with order norm of the M. And it's easy to show this is equivalent. I also need the definition of the Besov space and Triebel-Lizorkin spaces. Professor Siko just mentioned, but I need the analytical definitions. So we choose a Schwartz function phi 0 and satisfy such conditions. This is very standard definitions. And then we make a dilation phi to j power, just the phi 0 2 minus jx minus phi 0 2 minus j plus 1x. And then the sum of all j in z, this constitute a homogeneous partition of unit. So follow Professor Turbo, we use this notation S sub infinite. This means all the Schwartz function has Walsh moment for all orders. Then the homogeneous Besov space for all the parameters are defined in this way. F belong to B dot alpha PQRN. If and only if this quantity is finite, And this definition is in this way. We just note, so this is the homogeneous partition of unit. So we take any distribution f, then we make the Fourier form, and then we times phi to j, and then make the inverse Fourier transform, and then take LP long, and then we take the small LQ long, write it this way. So this is the definition for homogeneous Besov spaces. And if we change the order, then we got the homogeneous Triebel-Lizorkin spaces. But when p equal infinity, such definitions is more sensitive. Then we cannot use this way. Instead, this way we use this way. We take the average here. You see, for any ball, then here is the same. But the sum started from j equal m to infinity. So it's well known when q equal to p equal infinity, f dot 0 Rn is just the well-known BMO space, BMO Rn. And when smoothness is 0, q equal 2, then this space is just the hard space. And so if q equal 2, this is just the Sobolev spaces. And I also need the definition of the inhomogeneous Besov space and the Triebel-Lizorkin space. And for such spaces, the only difference is we did not make we did not divide the unit ball. I mean, here we take the sum, just j start from 0 to infinite, and when j is a natural number, phi tilde j is just the phi, it's the same as before, but the phi 0 is just the function also take, but not 0 here. Phi tilde 0 is just the phi sub 0. So then this sum is given inhomogeneous partition of the unity of the whole array. So then the definition of the inhomogeneous of Besov space and the Triebel-Lizorkin space, we just need to replace this distribution space by the Schwarz distribution space, and then replace this this partition unity by the inhomogeneous partition unity. And when p equal infinity, here this only difference is here. We take the sum start from j max m and 0, not from m to infinite. So it's well known the first order Harvard Sobolev space is defined as follows. Let X be a non-empty set, D a coarse metric. This means you have a constant bigger than 1 or equal to 1 here. And we always suppose mu is a regular Borel merger. Then for B between 1 and infinity, S between 0 and 1, the homogeneous fractional Harvard sublet space M dot SPQX is defined to be the set of all measurable functions f in locally LP, for which there exists a non-negative g in LP and a set E with measure 0 such that for any xy not in E, this inequality holds true. Means fx minus fg no more than dxy to some power s, and then times gx plus gy. We use this sample df to denote all the set of all such g. Then we define the norm of the homogeneous norm. F m dot sp is just the norm of g in LP, take the infimum. And we define the inhomogeneous Harvard Sobolev space, just take the intersection with LP, and the norm is just the sum. And when s equal 1, such space was introduced by Harvard. And when s between 0 and 1 was introduced by Professor Fu, and for subsets of Rn, and myself for metric measure space. And this is the purpose I just mentioned. And it was proved by Harvard in this purpose. when S equal 1, such space M dot 1 PRM is just the classical Sobolev space W dot 1 PRM, and it's well known this is just the Triebel-Lizorkin space with Q equal 2 here. And surprisingly, when S is smaller than 1, then in this paper I proved this space is just equal to F dot S P infinite Rn, not P2 Rn. So there exists a gap for Triebel-Lizorkin spaces. So this is a little bit surprising. And later, with Professor Koskola and my students, Zhou, in 2011, we improved the definition of the Hawash gradient. The main difference is here. In the definition of the Hawash gradient, we use the same function, no matter how far the distance. For all the x, y, we use one function g. And but now, when we introduce a series of functions gk instead of one function g. So this is much more close the definition of the first order derivative of u. So because now we have a series of functions gk, then we can define the homogeneous Hawash Triebel-Lizorkin spaces in this way. We first take the LQ for all the j, and then because this depends on x, then we take the LP. And if we change the order, then we got the Hawash Besov spaces. And then a question is, such spaces, if x just is the Euclidean space, why does such space coincide with the classical Besov space and Triebel-Lizorkin spaces? The answer is yes, but we wish to prove this in more general setting. So a more general setting is, so it's well known in metric space. It's well known setting is called space of homogeneous type, which was introduced by Koyman and Weiss. And what does it mean? Means the measure is doubling. Means the measure of 2r is controlled by the ball measure itself with a constant independent of the center x and the radius r. So then later also with Professor Mueller and also Professor Han, when we try to prove such Besov spaces coincide with the well-known Besov spaces on metric space, we need an additional assumption we call Lewis doubling condition. This means the ball with double radius is strictly greater than the measure of the ball itself. The constant C0 here is surely be greater than 1 and cannot be 1 because that's obviously. And there exist many examples of ROD spaces, especially all connected spaces of homogeneous type are ROD spaces. And the later such ROD spaces I just mentioned was introduced by Dr. Mueller and Professor Han with myself in this three purpose, and also with my student Zhou will give many equivalent characterizations for ROD spaces in this paper. And then with Koskara we proved if X is a ROD spaces, then we can prove what we just introduced the Hawash Triebel-Lizorkin space coincide with the well-known Triebel-Lizorkin space on such setting, and this space was introduced in this very long purpose. And also the same is true for the Hawash Besov spaces. Maybe I should mention that in this very long purpose, when we try to introduce the Besov space and the Triebel-Lizorkin space on such setting, we spend many pages to show such definitions is reasonable. But now we just give a very easy understand equivalent characterizations, pointwise characterizations, m dot SPQ and n dot SPQ. And such characterization was used to show the invariance and cross-confirm mappings of some function spaces in the paper with Koskala and Yuan. And later, such ideas was also some of ideas was also used by Koch and Koskala, Saxma and Sato in this paper, and Bank, Saxma and Sato in this paper, and later by Yuan and Zhou and myself in this paper. So, and more papers are concentrated study on this space I mentioned before by Koskolo and his collaborators. And now let's introduce the Ball average characterizations for the second Sobolev space. So I just introduced how to define the first order Sobolev spaces or metric major settings. But actually, till very recent years, 2012, Wedler and his collaborator and Marshall in this papers, they proved a very surprising characterizations. Let's first introduce the Ball average. For any t between 0 and infinity and g is locally function and x in Rn, we use this notation to denote the average of g on the ball. So such a definition can make sense for every metric major spaces because we only use the major and the ball and the major and nothing else. So then Professor Wedler and his collaborator the causes and proved these characterizations. When p between 1 and infinity, then f belongs to W2P_Rn, the second order Sobolev spaces, if and only if f in LP and there exists a function g in LP such that this function, this square function, belongs to LP. Please note, in such a characterizations, we do not use any derivatives of f, but indeed correct the second order Sobolev spaces. So obviously, this makes sense on any metric major spaces because you only use the Ball average. This means this function we define in this way: BTF minus f and over t square minus the another Ball average of another function g, and then take the square. This in LP. So this is very interesting. And then later with Wen Yuan and another student of mine, we try to prove this is true also for the Lugin average functions. So what do you mean Lugin average function? Compare this function, he only takes the square when t, we have the extra average here. So this is the ball, we take the integral for y, then we need to here this measure of this ball, and then we take the square, and then we prove if p be greater than 2 and infinite, then f in W2P_Rn, if and only if f in LP and there exists g in LP such that the average function in LP, and at that time when p is smaller than 1 and smaller than 2 and bigger than 1, we can only show when n equal 1 and 2 and 3, and this is also true. But we cannot prove when p is bigger than 4. And later, with Feng Dai, and then we improve our result. We can show part of them. So when n is greater than 4, and p between 2 and over 4 plus n and 2, then this is true. F in the second Sobolev space, if and only if f in LP and there exists a g in LP such that s fg in LP, and if p is smaller, this is between 1 and smaller this number, So because when n equal 4, this is just equal 1. So here n should be bigger than 4. Then this conclusion does not hold true anymore. So in some sense, but till now, we still don't know when p equals this endpoint, what happens. This is still open. So we don't know. And also we got the same conclusion for G lambda star functions. What's the difference with the area function? The area function will take here we take the integral on any ball, but for G lambda star function here we take the integral for the whole Rn. Then we have the extra decay factor here. So we got the same conclusion, and we have the same problem. It's still unclear on the endpoint case when p equal 2m minus 4 plus m. And we also got the same conclusion for any for all Sobolev spaces in this paper with Wang Yuan and my student Hu. And if you still remember the Hawash definition of the Sobolev spaces, he used some pointwise characterizations. So we ask the same question for the second of all the Sobolev spaces. Why do we have this some kind of pointwise characterizations? We give this answer yes. With Professor Dai, we proved when in F belong to WTPRn, if and only if F in LP, and also you can find the function G in LP, such that for any t, for any positive t, and almost every x in Rn, fx minus the average of f on the ball with the center x, radius t, no more than a constant times t squared here, and gx. And this is also equivalent to this f minus bt f epsilon over t squared, take the supreme is a constant. So, but we don't know such equivalent characterization is still true or not for space of homogeneous type. This is still not known. So, but we only can show if f in WTPRn, then both are equivalent. But because of course such a definition, this and this can be used as definitions for the second order Sobolev spaces on space of homogeneous type. This is no problem because we don't need any derivatives here. But then the problem is we don't know if they define the same space or not. This is not known. We can have more equivalence, but almost but the split is the same. We just take some average with more average here and with more average here. So this is not the essential. We can also have the sharp maximal or function characterizations, because the sharp maximal function is just some average, ball average. Use some ball average here. And a key lemma to prove such characterizations is the following. If phi is a Schwarz distribution and C tilde between 0 and infinite is a constant, then we can prove the limit of this quantity phi minus the average of phi on the ball with radius t times over t squared. This limit is just the Laplace of act on phi. So in some sense, we just use this to replace the second order derivatives of phi. So we just use this quantity to replace the second order of the derivatives of phi. So we have this same conclusion. If we take a value here, we got the same. So this is a key lemma for our proofs. Of course, we also need to use some subtle estimates for Fourier transform and something else. And also we can generalize all aforementioned characterizations of WTP-Rn. We can generalize to even all the Sobolev spaces. This is true, no problem. And so I just mentioned some open questions still not clear in this area. And then we use the same idea. We try to characterize the Besov space and the Triebel-Lizorkin space. Here is the conclusion. So I just recall the definition of the Triebel-Lizorkin space. If you use the analytical definitions, it looks very complicated. But now, actually, we can prove. But please notice alpha is between 0 and strict less than 2. We cannot get 2. Then, if fp between 1 and infinity, then f in the Triebel-Lizorkin space f alpha pq Rn, if and only if f in LP Rn, and this is finite. This means f minus the ball average of f with the radius 2 minus k, you find, and 2k alpha, you take first the L coulomb and the L coulomb. And if p is equal infinity, almost the same. We just replace here. And we also got the same conclusion for Besov spaces. So you first take the L coulomb, f minus b, the average of f in the radius with radius 2 minus g, and so it's not a problem to use this as a definition for the Besov space on any metric spaces, because this makes sense. And later we also got the little pilot characterizations for Triebel-Lizorkin space. So this is what we call the Lugin area functions definitions. You just take 2 times average and 2k alpha q, then take the sum. We can prove f in this Triebel-Lizorkin space if and only if f in LP and RF this function in LP when R is between 1 and q. And we can prove when R is here, when this is just the q equal q, then we have so here R should be strictly less than q. If R equal q, then we got this conclusion. Here we prove this. If alpha between 0 and 2 and p between 1 and infinity and q between 1 and infinity, then f in LP and AQF in LP. If then we can show f in this Triebel-Lizorkin space. Conversely, if p between q and infinity and alpha between 0 and 2, or p between 1 and q and alpha in this range, then f in the Triebel-Lizorkin space f alpha pq implies f in LP and the Lugin area function in LP. And we can prove if alpha smaller than this index quantity, this conclusion is not true. But if alpha equal this, what happens is still unknown. I also like to mention with Yuan, we also got the pointwise characterizations for the Triebel-Lizorkin and Besov spaces. So also instead of one function, we use here a series of function gg, and here fx minus the average of f with the center x and power 2 minus g. We call this alpha order Hawash gradient sequence. Then use this series of function gg, we can calculate the Triebel-Lizorkin space, but alpha is strictly less than 2. Then we can prove f in Triebel-Lizorkin space only if and only if f in LP and this quantity is finite. So here we just use GK. So we do not obviously use the derivatives. When the p equal infinity, this we need to make the suitable modifications. And we have the same conclusion for the Besov spaces. We first take the LP norm and then we take the LQ norm. So the main problem is what's applications for such characterizations. This is still don't know. I will use. I will very fast go to finish my talk in 7 minutes. So here we also try to establish the same characterizations for variable Besov and Triebel-Lizorkin spaces in both papers. And a new idea in this paper is we try to use the derivatives of ball average. Then we got a very interesting sense. If we put a derivatives on the radius here, this is a new faculty. Then we can use the pointwise characterization. We can get the W4 PRM, can correct the W4 PRM. So I just stated for you, if we don't use here, this we can only correct the Sobolev spaces W2 PRM. If we put one derivatives here, then you get 2 orders more. And if we put the second order, then you get W6 here. So actually, in the metric space setting, they have another famous when all the Sobolev spaces they called the Newtonian spaces, which was introduced by Galikan. Instead, the Hawashi gradients, he used the upper gradients. Here's the definitions. You know, the Hawashi gradients means fx minus fy no more than dxy times gx plus gy. Here, so they just straight lines connected both points. But the upper gradients, he required this should be true for all most good curves, gamma. So this is very strong, quite strong. But such a definition has a very good advantage. Has a strong locality. This means if a function is a constant on a measurable set, then we can take the upper gradient to be 0, almost area on that set. However, we cannot take the Hawash gradient to be 0, almost area on that set. So in some sense, the upper gradients introduced by Hanolo-Koskora is actually more close to the has properties more close to the derivatives. And we use the same ideas. We generalize the we also introduce the Newton Besov space and Newton Triebel-Lizorkin spaces. And somebody also did the Newton type origin spaces. And also Hawash actually the consented also such a characterization. Instead the ball average, the consider the average on the sphere, but such characterizations is not useful for metric measure spaces. Okay, let's just stop here. Thank you for your attention.
Would you like to ask some questions? So we thank Dachun.